The sun. Here are our learning goals for today. Explain the source of the sun's energy. Describe the different layers of the sun and their characteristics, the core, the radiative and convective zones, the photosphere, chromosphere, and corona. Describe the solar features, sunspots, prominences, solar flares, and solar wind. Alright, the sun is the closest star to the Earth. It's about 93 million miles away. It's an average star. There's nothing special about our sun, and that's a good thing for us. As we'll learn later, being an average star has given time for life to evolve on this planet. However, our sun is enormous compared to the Earth. We could fit 1 million Earths inside the sun. And the sun's composed primarily of hydrogen. Gravity is constantly trying to collapse the sun. The sun is an enormous object, and it has tremendous gravity. And that gravity is trying to squish the sun down into a tiny, tiny, tiny ball. And that creates enormous heat and pressure in the center or the core of the sun. Because of that enormous heat and pressure, hydrogen atoms are able to fuse together to perform fusion and form helium. So, hydrogen atoms under enormous heat and pressure will fuse or join together to form helium. And whenever hydrogen atoms fuse together to form helium, they release an enormous amount of energy. Einstein came up with his famous equation: energy is equal to mass times the speed of light squared. The speed of light is 186,000. If we square that, that's a ginormous number. So even the tiniest little amount of matter can be turned into a huge amount of energy. And the sun does this. Whenever whenever hydrogen atoms fuse into helium, there's a tiny, tiny amount of matter that's lost. And that is equal to a huge amount of energy. So every time these atoms fuse together to form helium, the sun receives a tremendous amount of energy. That's the same energy and the same thing that goes on inside a hydrogen bomb. So every second, it's like millions of hydrogen bombs going off inside the sun. And that outward force from fusion balances the inward force of gravity, and the sun remains stable. The outward force from the fusion of hydrogen to helium counteracts the inward force from gravity, and the sun stays stable and balanced. If fusion stopped, gravity would take over and crush our sun into a tiny little object. If there was no gravity, the sun would explode. But the two forces are balanced, so the sun remains stable. Alright, hit pause. When you're ready, hit play, and I'll give you the answers to these questions. What is the source of the sun's energy? The sun's energy comes from the fusion of hydrogen atoms into helium atoms. When that happens, a tiny amount of energy is lost. That's created into a huge amount of energy. What is the main fuel the sun uses to produce its energy? That fuel is hydrogen. The sun fuses it to form helium. The formula mc squared tells us that a tiny amount of matter lost when hydrogen atoms fuse into helium produces a huge amount of energy. Why doesn't the sun collapse from its own gravity? Because the outward force of energy released by the fusion of hydrogen atoms into helium counteracts the inward force from gravity, and the sun remains stable. Let's look at the layers of the sun. We're going to start at the center, so the first one we're going to look at is the core. It's extremely dense, it's extremely hot, at least 15 million degrees. Those are the conditions that are necessary for hydrogen to fuse into helium, and that's where fusion takes place. This is where the core is located, right in the center of the sun. The next layers we run into are what we call the radiative and convective zones. And they transfer heat and radiation between the core and the photosphere. The photosphere is the outer surface of the sun, you might say. So the radiative and convective zones just transfer the heat and energy and radiation outward to the outer layer of the sun. We're not really going to talk much more about them. You just need to know they're there and what they do. Okay, so this whole area between the core and the very surface here of the sun are the radiative and convective zones. The photosphere is the visible surface of the sun. When you look at the sun, you see the photosphere. Photo means light, so think of it as the surface of the sun that you see. And the photosphere is yellow. And it's important that we know the color of the different layers now as we talk about them going outward from the photosphere. So the photosphere is yellow. And it's about 6,000 degrees. The two temperatures that I really want you to remember about the sun are the core, which is at least 15 million degrees, and the photosphere, which is about 6,000 degrees. So there's a huge temperature difference between the center of the sun and the surface. Right, so on this diagram, this is the photosphere, this little area right here. And when we look at the sun, that's what we see. So this would be the photosphere here. Here's a picture of the setting sun. It's safe to look at the setting sun. It won't hurt your eyes. So this yellow disk is the visible surface of the sun. This is the photosphere. All right, the next layer out is called the chromosphere. Chromo means color, right? It's the inner part of the sun's atmosphere. It goes out thousands of miles above the photosphere, and it's red. It's important that you remember that the chromosphere is red. It's about 20,000 degrees, but it's really not that critical that you remember that. So on this diagram, you can see this reddish haze here all the way around the sun. That's the chromosphere. And if we look at the sun in a telescope with a special filter, we can see the chromosphere. And this is the chromosphere here, this reddish haze that surrounds the sun. It's the inner part of the sun's atmosphere. The corona is the outer part of the sun's atmosphere, and it extends out millions of miles above the chromosphere. So it's a really big thing. And we can see it only during a total solar eclipse. And it's very much hotter than the chromosphere, or the visible surface of the sun, the photosphere. And in this diagram, this is the corona. Corona means crown, so it looks kind of like a crown around the sun. This is the outer atmosphere of the sun. And here's a picture from a total solar eclipse. It's the only time you can see the corona with your naked eye. The rest of the time it's covered up by the glare from the photosphere, from the visible surface. There's so much light coming out of the sun that it overwhelms the light from the corona and you just can't see it. But this is the outer atmosphere of the sun. All right, hit pause, answer these questions, and when you're ready, hit play. What are the conditions in the core and what happens there? Well, it's extremely hot, around 15 million degrees. Matter is compressed due to the tremendous gravity, so it's very, very dense. And nuclear fusion happens there. Hydrogen is turned into helium, and that's where the energy of the sun is generated. What happens in the radiative and convective layers? Well, they transfer radiation and heat and energy from the very hot, dense core of the sun to the outer layers, especially the photosphere of the sun. What is the photosphere and what color is it? Photosphere is think of it as the outer surface of the sun. It's the visible surface of the sun. It's what you see when you look at the sun, and it's yellow. What is the chromosphere and what color is it? The chromosphere is the inner atmosphere of the sun, and it's red. And what is the corona? The corona is the outer atmosphere of the sun. So let's look at some features of the sun. First thing we're going to talk about are sunspots. And they're exactly what their name says. They're spots on the sun. And when you look at the sun, you can see them sometimes with your naked eye, like near sunset when it's safe to look at the sun. If you have really sharp eyes, you might actually see some sunspots. But they're dark black spots on the photosphere. Right? They're slightly cooler than the rest of the photosphere. That's why they show up black or darker. And sometimes there's very few sunspots, and sometimes there's lots and lots of sunspots. When there's few sunspots, we call that solar minimum. Minimum means few or none. And when there's lots of them, we call it solar maximum. Maximum means a lot. It's about 11 years between the solar minimum and the solar maximum. The sun goes in a cycle. So about every 11 years, we have a solar maximum. There's lots of sunspots, and then they go away. And we have a solar minimum, where there are very few sunspots, and it's related to the magnetic activity that's going on inside the sun. So there we go. So when we look at this diagram of the sun, these are sunspots, these little dark areas here. They're on the photosphere. They're due to magnetic things going on inside the sun. They're darker because they're slightly cooler. Here's a close-up from a telescope. They're really complex. And here's two photographs of the sun. This is during solar maximum. You can see all these sunspots. They're all over the place. And here's solar minimum. There's none, or there might be one, but there's very few. It's about 11 years between these two. We're going to learn later that the number of sunspots on the sun influences our climate because it changes how much energy the sun produces. So these sunspots we'll talk about again when we talk about weather and climate. Another thing on the sun are called solar prominences. Magnetic storms cause material in the chromosphere to rise up and then fall back to the sun. It makes like a loop. And they're red. And on this diagram, you can see they're in the chromosphere, but magnetic storms cause material here in the chromosphere to rise up, and then it falls back. And when it does that, it makes this kind of a loop thing. Okay. And here's a special picture of the sun taken with a telescope with a special filter on it. And here's the reddish chromosphere, the inner atmosphere of the sun. And a magnetic storm has caused the chromosphere to rise up, and then it falls back. And when it does that, it makes a loop. Now, solar flares are different. They're caused by magnetic storm, but these things are way different. A solar flare causes huge amounts of energy to leave the sun and travel through space. These things can be really dangerous for us here on Earth. They bring radiation and all kinds of bad stuff, but they can also destroy electrical equipment, and they can cause power failures. They can mess up radio interference. And your cell phone works off a radio, so if they're really bad, your cell phone might not work right. Okay, and here's a picture of the sun, and this is a solar flare. Now, prominences are just little bitty things that rise up from the chromosphere and fall back and don't cause us any trouble. But this is big bad news if it hits the Earth, right? A really bad solar flare directed at the Earth could destroy our power lines and all our electronic infrastructure. And luckily, in the last 100 years or so, since we've had those things, this hasn't happened. But one day it will, and when it does, we won't have electricity for months, weeks, or maybe even years. So that could be a huge disaster for us here on the Earth. And the last thing we're going to talk about is the solar wind. There's a constant stream of electrons and protons that leave the corona, or the outer atmosphere of the sun, and move away from the sun in all directions. Now, this is a very gentle thing. It's been going on since the sun was born, and it's not harmful to us. It's way different than a solar flare. Okay? And the good news for us is that Earth has a magnetic field, and it deflects this gentle stream of charged particles, electrons and protons, that leave the sun constantly. If we didn't have a magnetic field, the solar wind would eventually erode away our atmosphere. Right? Now, some of that solar wind is directed by the magnetic lines of Earth's magnetic field and actually hits our atmosphere at the poles, and when it does, it causes the northern lights, or the auroras. Right? So here's a diagram that shows the sun, and then this gentle leakage. Think of it as the sun just leaking electrons and protons, and they just travel gently through space. They don't cause any problems. So this is just kind of a diagram trying to show you that these particles are leaking from the sun in all directions all the time. Right? And when they hit our magnetic field, they're deflected away from the Earth. But some of them end up following these magnetic field lines and hitting the poles. And when they do, then we get the northern lights and the southern lights. And here's a beautiful picture of the northern lights, or we also call those aurora. So this is the charged particles are hitting part of our atmosphere and making this beautiful display. All right, hit pause, answer these questions, and when you're ready, hit play. What are sunspots and what causes them? Sunspots are dark areas on the photosphere, or the visible surface of the sun, and they're caused by magnetic influences within the sun. Solar prominences are when magnetic storms on the sun cause part of the chromosphere to rise up and fall back to the sun, and they make kind of a little loop. And the chromosphere is red, so solar prominences are red. What is a solar flare, and why could they mess up your life? Excuse me. A solar flare is caused by a magnetic storm on the sun, and a huge amount of energy is released by the sun with a solar flare. And if there's a really big solar flare and it's directed straight at the Earth, it could destroy our electric infrastructure here on Earth. What is the solar wind, and what protects us from the solar wind? Excuse me. The solar wind is a gentle leakage of protons and electrons that goes on constantly in all directions from the sun, and it strikes the Earth's magnetic field and then is directed away from the Earth by the Earth's magnetic field. If you'd like, you can go to this address and watch a real nice video about the sun, but I can't put it in this video that I'm making now.